When you've completed this lesson, you should be able to understand the concepts of ratio, proportion, and percent, and solve problems that involve ratio, proportion, and percent. Photonics technicians need to work with these things because, for example, in scale drawings, you'll encounter scales of 1 inch to 400 feet. Or in beam divergent problems like this one, you'll have a formula of the square root of A1 over L1 is equal to the square root of A2 over L2 that relate the beam's cross-sectional area to the distance along the beams. So here's an example scenario that photonics technicians might encounter. Suppose you have a far-field beam from a carbon dioxide laser that appears to radiate from a point source within a laser cavity. At a distance of 3,000 meters, you measure an irradiance, E is equal to 35.6 watts per centimeter squared. What would be the irradiance at a distance of 8,000 meters? And if the beam image is circular with radius at 0.8 meters at 8,000 meters, what is the total power of the beam that's coming out of the laser? We'll return to this problem after reviewing some of the skills in this module. Ratios are quantitative comparisons of objects and values. So let's consider these example ratios. So we have Bill and Jill. Bill is twice as old as Jill, so the ratio of Bill's age to Jill's age is 2 to 1, or 2 over 1, or 2 divided by 1, or 2 colon 1. So we know if Bill is 2 years old, then Jill must be 1 year old, or if Bill is 10 years old, then Jill must be 5 years old. Alright, so that's a pretty simple one. Let's take one that's a little bit more technical. Suppose we have a large driven gear that has 4 times the number of teeth as a 10-tooth drive gear. So that means that the gear ratio is 40 to 10, or we can write that as 40 over 10, or 40 divided by 10, or 40 with a colon and then 10. So we notice that you can reduce these ratios to 4 to 1. Now, there's different ways to express ratios, as you've seen in the previous slide. So we can say that Bill is twice as old as Jill, and any one of these will communicate that. We can say that the driven gear, that's 4 times as many teeth as the drive gear, and any of these would communicate that. Or we can have donuts that are on sale at half price, so 1 to 2, or half, or 1 divided by 2, or 1 colon 2. So sometimes you find that we have units that don't match. So for example, we might have 15 minutes over 1 hour, or 2 teaspoons over 4 cups, or 3.5 centimeters over 1,000 meters. In that case, we can use a unit ratio to convert to consistent units. For example, 15 minutes per hour, we can multiply by 1 hour over 60 minutes. This is a unit ratio that you've seen in a previous module. And we pull out the values, 15 times 1 and 1 times 60, and the units over here, and you notice that all of the units will cancel. So that leaves you with a ratio of 15 over 60, or that we can reduce to 1 over 4. Now, this only works when the quantities are related. So, for example, in our example here, we had 2 time quantities. In the second case up here, we can do the same thing since they're both volume measurements for baking. And the third example are length measurements, so we can multiply each of those by unit ratios and leaving only the numbers as a result. Now we always want to reduce the fraction to its lowest terms, as we did here. The result is 15 over 60, but we can see here that we can divide both numerator and denominator by 15, then we would end up with 1 to 4, which we've done to reduce that in the lowest terms. Sometimes units in a ratio are not related. Not all time units, or not all volume units, or not all distance measurements. So, for example, 360 miles per 8 hours, or the ratio of 14 gallons to 3 minutes, or $26,995 to 10 years. Now, you can imagine where all of those ratios would appear. In such cases, the numerical part of the ratio can sometimes be reduced to lowest terms. So we'll take the 360 miles divided by 8 hours, and we can reduce that to 45 to 1 miles per hour. Or you can use unit ratios to convert to different units. For example, and you've seen this in the previous modules, when we take 14 gallons to 3-minute ratios, multiply it by the ratio of 1 minute over 60 seconds, which will effectively change the minutes to seconds, because we know that the minutes will cancel, and multiply by 1 cubic foot per 7.48 gallons, noting that the gallons will cancel, leaving us with cubic feet. So we multiply all the values together and the units together, and as we planned, cubic feet and seconds are the only thing that remains in the units. So we're left with 14 over 1346.4 feet cubed per second. Or if we evaluate that ratio, it's 0.0104 cubic feet per second. Now, a percent is just a special ratio that compares numbers of parts to 100 equal parts. So out of 100 pencils, for example, if 10 are red, then the ratio of red pencils to the total is 10%. So you probably figured that out without using your calculator. Or if 37 are green, then the ratio of green pencils to the total is 37 to 100, and 37 green pencils to 100 total pencils, which we can write as 37 to 100, or as we evaluate it out, we know that it's 37%, which is green. Percents are pretty easy to work with, but you don't always have ratios that are compared to 100. Sometimes the ratios are compared to other numbers of equal parts. So, for example, suppose we have 1 out of 6 equal parts. What percentage is the one part? Well, we write the ratio as a fraction and convert to a percentage. So we have 1 to 6 is the ratio, and we can just multiply that by the unit ratio of 100% over 1, and we'll end up with 0.16667 times 100%, or 16.7%. Now, this is the mathematically correct way to handle the conversion, but you know that you're just multiplying the 1/6 times 100%, which is probably the way that you're used to seeing it, and that's quite all right. So 1 out of 6 is the same as 16.7%. Now, what would the percent be for 3 out of 6 parts? Can you think through that one? Well, without actually showing it on the screen here, I bet you already know that 3 out of 6 is going to be a ratio of 0.5 times 100%, which is 50%. Good for you. Now, proportions are equal ratios. So the concept of a proportion is very important to mathematics and very important for you in solving your problems in photonics. So we have, for example, two ratios, 4/2 and 10:5, and those are said to be proportional because they're equal. 4/2 is equal to 10/5. They both have a value of 2. So here are some equal ratios that are all proportional. So 4/2, 10/5, 8/4, 12/6, and 20/10. Interestingly enough, these are also proportional. So can you tell what the difference is? I've just inverted the numerators and denominators in all of these. So 2/4 and 5/10, 4/8 and 6/12 and 10/20 and so on. So those are also all equal ratios. Ratios that are not equal are not proportional. So for example, the ratio of 2/4 is not equal to the ratio of 1/3. So we would say that 2/4 is not proportional to 1/3. Now, equal ratios have a nice thing called a proportionality constant to equal that constant. So as we saw earlier, 4/2 and all of these other ratios all equal 2. So here's an example. Suppose we have a spring that's rated by its spring constant, the ratio of force needed to stretch the spring a certain distance. You'll see here that that constant is equal to the ratio of F1 to D1, or F2 to D2 if the string is stretched, and so on. And so we have lots of different proportions that can come out of that, but it's always equal to K if the spring maintains its elasticity. So let's look at that spring a little more closely now. So a certain spring requires F equals 10 pounds to stretch 2 inches, and force of 20 pounds to stretch 4 inches. So we can set up two different ratios, right? 10 pounds to 2 inches and 20 pounds to 4 inches. I believe that you can see that the value for both of those is 5 pounds per inch. There's a constant proportionality present in this relationship. Interestingly, you'll notice that if you plot the distance of the stretch versus the force, as the distance gets bigger, the force gets bigger, and they all fall on a straight line. So what do you think you know about that straight line? It looks a little bit like the slope, doesn't it? We're going to determine a little bit later in this course that the slope of the graph to the force of the distance is, in fact, the spring constant. Now let's return to that opening scenario where we had the beam being spread by an angle theta. We've noted that there's a ratio called tangent that you'll learn in a later module in this course, which is equal to the opposite over the adjacent side of a right triangle. Now, on this particular triangle up here, we have that the angle is theta over 2. If the entire angle of the beam spread is theta, then half of it will be theta over 2. And the tangent of that angle equals the opposite side of the triangle over the adjacent side, the side that's adjacent to the angle. So we set up that proportion here, that the tangent of the ratio of those two sides is always going to be, for example, for the small rectangle down here, d3 over 2, half of d3 divided by the distance of the adjacent side would be 3,000 meters, or for the big triangle, it would be d8 over 2, half of that divided by this distance, which is the 8,000 meters. So we can see that the divided by 2's will cancel out, and what we're really left with is two ratios, d3 over 3,000 meters equals d8 over 8,000 meters. And we can rearrange it by multiplying and dividing by the different terms, and we'll end up with d3 over d8 is equal to 3,000 to 8,000 meters, or the constant of proportionality of 0.375. Now we're told that the irradiance E varies inversely with the target's cross-sectional area. So the cross-sectional area is going to be pi divided by 4 times the diameter of the beam squared. So we can write that the irradiance from position 8 to the irradiance of position 3 is equal to, inversely, so we'll have the area position 3 divided by the area position 8. Notice that because it's an inverse proportion that we've got reversed subscripts on our formula. So now we can substitute in the area calculations as pi over 4 times the diameter of the position 3 squared and pi over 4 times the diameter of position 8 squared. And you'll notice that the pi over 4's will cancel. And then we're just left with the ratio of d3 squared to d sub 8 squared is equal to the ratio of the irradiance of E sub 8 over E sub 3. Again, notice that they're inversely proportional. We can just solve for the irradiance at position 8, and we'll end up with d sub 3 over d sub 8 squared times E position 3. So now let's substitute in our irradiance that we're given and the constant ratio that we found. And square that and multiply that by the input irradiance of E3, and that was 35.6 watts per centimeter squared, and we end up with a 5.01 watts centimeter squared. With a beam diameter of 160 centimeters, we're asked to find the power at position 8. To do that, we'd multiply the power of the beam is equal to irradiance times its area. Okay, and so the irradiance at 8, which we just figured out, and the area at 8, which we're going to calculate. We'll substitute in those values. 5.01 watts per centimeter squared, pi over 4 times 160 centimeters squared for the diameter. And we'll group the numbers and the units, and the centimeters squared will cancel. and the result will be just watts. So we're left with 101,000 watts, better known as 0.1 megawatts. Okay, so let's look at some practice exercises to see if we can use these skills for some real-world application. Now, as before, we're not going to go through every single problem, but we'll do just enough to give you the confidence to complete the rest on your own. First of all, let's look at exercises 2, 3, and 4. They're all related, so we'll just cover them quickly. So what is the ratio of shaded to unshaded areas in this problem? Well, that would be the count of the number that's shaded divided by the count of the number that's unshaded, which would be 12 to 8. So we can write and reduce that and divide both of those by 4, and we'll end up with 3 over 2. So the ratio is 3 to 2, which we can write many different ways. Next we're asked, what's the percent that's shaded? Well, if we have 12 parts shaded and 20 parts total, then we have 12 to 20, and we want to go ahead and multiply that by 100%, and the result is 60% shaded. And the percent unshaded is 8 parts to 20 parts, which is 40% unshaded. And you'll notice that, of course, what's the sum of the percent shaded and the percent unshaded? As it should be, it's 100%. Here's the second figure. What's the ratio of shaded to unshaded again? Again, how many are shaded for? How many are unshaded for? So we have a ratio of 1 to 1, which we can write 3 different ways. The percent shaded, you can probably know this without thinking about it, is 4 parts over 8 parts, which is the same as 50% shaded. And I'll bet that you know already what the percent unshaded is. Sure enough, it's also 4 parts over 8 parts, which is also 50% unshaded. Okay, so we have one more figure to look at, and that'll be the square figure that is shaded in half. Now, this one's a little more tricky because it doesn't have a number that you can count. So what's the ratio that's shaded to unshaded in this case? Well, we've noticed that they're equal total areas that are shaded and unshaded. So we don't really care what number they are. It's going to be 1 to 1 because they're both the same. So the percent shaded is clearly half of it shaded, better known as 50%, and half is unshaded, which is also equal to 50%. Now, exercise 6 asks you to look at some solders that's made of 6 parts tin and 4 parts lead. So, very common percentage, and that is for every 10 parts of solder total, there are 6 parts tin and 4 parts lead. So this is just like the figures that we saw earlier. You can draw yourself a box with 10 parts in it and color in 6 parts for the tin and 4 for the lead, and you would be just like the previous exercise. So in 1 kilogram of solder, how much of it is tin? Well, we'll set up a proportion equating 2 ratios. X for the number of grams tin is related to 1,000 grams of solder, as we know the ratio of 6 parts tin to 10 parts solder. So now we just need to solve for the unknown parts, and as you've learned in the previous module for solving for proportions, you can multiply both sides by 1,000, and on the left side, the thousands will cancel, leaving us with just the x that we're looking for, and on the right, we'll have to multiply all of those parts together. So we're left with 6 times 1,000 divided by 10, and the parts cancel and the solder units cancel, so we're left with grams of tin. So 600 grams of tin. And of course, you'll know that the next question will be how much of it is lead. So we'll set up again our proportion equating 2 ratios as before. This time, the grams x will represent the numbers of grams lead in 1,000 grams, and 4 parts lead to 10 parts solder is the equation that we'll equate to. So we'll solve for the unknown part of the proportion by multiplying both sides by 1,000, and we'll be left with this value. And 4 times 1,000 divided by 10 with the units canceling again, and this time we'll have 400 grams of lead out of 1,000. Now, exercise 7 asks you, which of the ratios is proportional to the ratio 40 to 5? Well, proportional ratios are equal, so test that theory with each ratio. So is 20 to 10 equal to 40 to 5? Well, we multiply both sides by the denominator, or cross-multiply. So we multiply 20 over 10 times 10 and 5, and 40 over 5 times 10 and 5. The 10s will cancel, and we'll be left with 20 times 5, and the 5s will cancel, so we'll be left with 40 times 10. Do you see now why we call it cross-multiplying? Well, it's the same as multiplying 20 times the denominator of the other fraction and 40 times the denominator of the first fraction. So that's a shortcut that we'll be able to use instead of having to go through this process up at the top. So we're left with 20 times 5 is 100 and 40 times 10 is 400. So since these are not equal, the answer is no. 20 to 10 is not equal to 40 to 5. Now here's the second ratio. 8 to 1, is that equal to 40 to 5? Well, again, we'll cross multiply. 8 times 5, is that equal to 40 times 1? So 40 equals 40, so yes, 8 to 1 is equal to 40 to 5. Those proportions are equal. A third example is 5 to 40 equal to 40 to 5. Well, if we just invert one of them, does that make it equal? So we'll cross multiply again, just like we did before, 5 times 5 and 40 by 40, and it's pretty easy to see that those are not equal, so the answer is no. 5 to 40 is not equal to 40 to 5. And the last one that we can look at, 80 to 11, is that equal to 40 to 5? Well, it might be close, so let's see. 80 times 5 and 40 times 11 is 400 to 440, so no, they're not equal. Now, what is the constant of the ratios 1 to 8 and 8 to 64? Well, if the ratios are proportional, then the value of either ratio is the constant of proportionality. So let's first check if those ratios are proportional. Just like we did in the previous exercise, is 1 to 8 equal to 8 to 64? We go ahead and cross multiply, and sure enough, 64 equals 64, so yes, they are proportional. And the constant of proportionality would be the reduced fraction that we would get out of those, which is 1 to 8, or a value of 0.125, which is actually also a fraction. It's a decimal fraction. So let's look at exercise 12, which asks us to look at a scale drawing that's drawn at 1/4 inch to 1 foot in real life. So we're asked, what's the ratio of the scale drawing? Well, we can write it in many different ways. It can be 1/4 inch to 1 foot, or 1/4 inch to 1 foot, or we could change the units and we could say 1/4 inch to 12 inches, or 1 inch to 48 inches. Right? We multiply both of them by 4 and get rid of the 4 and get 1 inch to 48 inches. Or since we have both of them in inches, we can just say the ratio of 1 to 48. So the scale drawing is 1 to 48. Now, how long of a line would represent a 24-foot wall? Well, we're going to have to apply our proportion and our ratio. So we set up a proportion for the drawing dimension to the real life dimension is equal to the proportion of the scale of the drawing, which is 1 to 48. So let's substitute our values in. So we have 24-foot wall in real life, which we then can multiply out to solve for the drawing equals 0.5 feet or 6 inches. So a 6-inch line on the drawing would represent a 24-foot wall. We can go the reverse. How long would a duct be that's depicted by a 9.5-inch line on the drawing? Well, now we just have a different ratio. We have the real life to the drawing is equal to 48 to 1. Alright, so I'm sure that you take note of the relationship. So we have a constant of proportionality, right? So we substitute in our drawing dimension, that's 9.5 inches. Multiply that out, and we end up with 9.5 inches times 48, which is 456 inches, or 38 feet. Now, here's a good exercise. A hand-operated winch features a worm gear and a drum gear with a 41 to 1 gear ratio. For a 1.5-inch diameter drum, how many turns of the crank are needed to reel in 18 inches of cable? So each turn of the drum is 1 circumference. and a circumference is equal to pi times its diameter, which we're told is 1.5 inches. So the circumference is 4.71 inches. So we need 18 inches, and each turn is going to be 1.71 inches. So how many do we need? So we divide both of those numbers together. 18 divided by 4.71 per turn, and we end up with 3.82 turns of the drum. So now, how many turns of the crank are needed, which is the question. So not how many turns of the drum. So how many turns of the worm gear, and the ratio of turns of the drum we're given is 41:1. So we can set up that proportion and then substitute in our known value of 3.82 turns, which is the number of turns of our drum. So how many turns of our worm gear will we get out of that? So if we multiply that out to solve for turns of worm gear, we have 41 times 3.82 turns, and that ends up with 157 turns. So if you can turn that crank 40 turns per minute, how long would it take you? Well, 40 turns per minute is another ratio, isn't it? So 40 turns over 1 minute equals 157 turns at X number of minutes, and we want to find out what that X is. So we cross multiply, and we get 40 turns times X equals 157 turns times 1 minute, and we're going to solve for X by dividing both sides by 40 turns, and we have 157 turns divided by 40 turns times 1 minute, and the result will be 3.9 minutes. So it'll take you almost 4 minutes to reel in 18 inches of cable with this one gear. So that concludes our module on ratios and proportions. I now know that you have the confidence to complete the rest of these exercises. See you next time.